Now, in this video, we'll be looking at ionization energy, a property of elements that describes the amount of energy required to remove 1 mole of electrons from 1 mole of isolated gaseous atom to produce 1 mole of gaseous ions. But our focus in this video is on exceptions to the general rule guiding the trends or patterns of ionization energy values of elements on the periodic table. Now, if you look at this diagram provided from lithium to neon, there is a general increase in the ionization energies of these elements across the period. That is, from lithium across the period to neon, there is a general increase in the ionization energies of these elements, as you can see in this diagram. And it is no different in the third period from sodium to argon. But in the second period, we experience a discontinuity in the ionization energies between beryllium and boron and between nitrogen and oxygen. And in the third period, from sodium to argon, we experience a similar discontinuity between magnesium and aluminium and phosphorus and sulfur. What is accounting for this break in the trend? Or what is accounting for this discontinuity? Let's write the electronic configuration of beryllium, boron, nitrogen, oxygen, magnesium, aluminium, phosphorus, and sulfur. And so here the electron configuration and orbital diagrams of beryllium, boron, magnesium, aluminium, nitrogen, oxygen, phosphorus, and sulfur has been provided. And here let me indicate against them their ionization energies. For beryllium, we have for boron, magnesium, for aluminium, for nitrogen, oxygen, phosphorus, then sulfur. So we have the ionization energies of these elements. But the question is, why these exceptions to the general rule? Ordinarily, boron should have a higher ionization energy than beryllium if we are to go by the general rule. And we are expecting oxygen to have a higher ionization energy than nitrogen. Aluminium is expected to have a higher ionization energy than magnesium if we are to go by the general rule. But these are exceptions to the general rule. So what is accounting for that? Now, the 2s orbital of beryllium is completely filled. Completely filled orbitals have a greater and more stability than partially filled orbitals, as we have here in boron. So one would expect that removing an electron from the 2p orbital of boron would require less energy so to do. So because of the stability that completely filled orbitals grants the electrons over here, removing an electron from beryllium require more energy than removing this electron in boron. It is also important to note that the 2s orbital has a better penetration than the 2p orbital. It means that the 2s orbital of beryllium is closer to its nucleus than the 2p orbital of boron. So the closer the orbital is to the nucleus, the greater the attraction of the nuclear charge on the electrons occupying it. And so one would expect that the electrons in the 2s orbital for beryllium is more tightly held by its nucleus than the electron in the 2p orbital of boron. It would mean that it would require less energy to remove an electron from the 2p orbital of boron. Different orbitals have different levels of shielding of the nuclear charge. Now, the electrons in the 2s orbital of boron shields off part of the nuclear charge and makes it easier removing an electron from the 2p orbital. And so for this combination of reasons, removing an electron from the 2p orbital of boron requires less energy than removing an electron from the 2s orbital of beryllium. Now, between magnesium and aluminium, the same set of reasons that applies between beryllium and boron applies to magnesium and aluminium. The 3s orbital is completely filled, and completely filled orbitals provide stability to the electrons that are located in them. The 3p orbital is partially filled, and it will make this electron over here unstable, and for that reason it would require less energy to remove this electron compared to removing an electron from the 3s completely filled orbital. The 3s orbital has a greater penetration than the 3p orbital. It would mean that electrons in the 3s orbital will have a stronger attraction from the nuclear charge compared to electrons in the 3p orbital, which are slightly further away from the nucleus. Again, electrons in the 3s orbital will provide a shielding effect of the nuclear charge on this electron, and it will make this electron relatively easier to remove. So the combination of reasons that accounts for why the ionization energy of boron is lesser than that of beryllium applies here, why the ionization energy of aluminium is lesser than that of magnesium. Now, between nitrogen and oxygen and phosphorus and sulfur, the 2p orbital of nitrogen is half filled. Now, half filled orbitals and completely filled orbitals grants electrons occupying them stability. And so for nitrogen, removing an electron will mean doing so from an atom with a very stable electron configuration, as the orbital diagram is showing here. The 2p orbital is half filled, which means symmetrical electron distribution, and that grants stability, as compared to oxygen over here, which shows an asymmetrical electron distribution, and which means instability. And so with regard to oxygen, apart from the asymmetrical distribution of electrons, removing an electron would mean removing it from an electron pair over here that will be experiencing electron-electron repulsion. Now, repulsion enhances removal. And so because of that, makes removing an electron from oxygen requiring less effort and less energy compared to removing an electron from nitrogen. The same reasoning applies to phosphorus and sulfur. Removing an electron from phosphorus would mean doing so from an atom with a very stable electron configuration, as the orbital diagram here shows. That the 3p orbital is half-filled, and half-filled orbitals provide stability, compared to sulfur over here, which is showing asymmetrical distribution of electrons, which causes electron-to-electron repulsion over here, and by implication, repulsion enhances removal and makes it easier removing this electron over here, requiring less energy and less effort so to do, compared to removing an electron from a stable electron configuration phosphorus. So from the diagram, we see a general increase in the ionization energy of elements from left of the periodic table to the right. On the third period, from sodium to argon. On the second period, from lithium to neon. But there are exceptions to this general rule, and these exceptions are attributed to the unique electron configuration of these elements, which grants them either stability or instability, and makes it easier to explain why the ionization energy of boron is less than that of beryllium, aluminium less than that of magnesium, oxygen less than that of nitrogen, because of the asymmetrical electron distribution compared to the stable electron configuration of nitrogen, and so applies to sulfur, having an asymmetrical electron distribution over here with electron-to-electron repulsion, and that enhances removal, as compared to phosphorus having the half-filled orbitals granting it stability. So this is the end of my video. Thank you very much for watching, but keep watching.